Hello, my name is Frank Soboczenski. I'm a computer scientist at the University of York, and in this video we look at artificial intelligence and health. In particular, we're going to look at transformers, what they are, how they work, and why they are so popular. So if you think about transformers, the first thing that may come to your mind is probably the movie Transformers or the comic ones, but we are not talking about those. This image here is actually generated by generative AI. We're actually talking about this transformer, which is a language model. Pretty clear, right? Well, maybe not. There's lots of information in that diagram, but don't worry about this. We're not going to go into those technical details. We're going to have a high-level view on what transformers are and how they work. So you may have heard about transformer models such as GPT-2, GPT-3, GPT-4, or a very popular currently called ChatGPT. But do you spot something peculiar about the naming of those transformers? Let's have a closer look at what GPT actually means. GPT actually stands for Generative Pre-trained Transformer. Generative because the model is able to generate new content, new text out of the data, the existing data that it has learned. Pre-trained because normal transformers, when you create a new one, you need to train them on a lot of data. It's sometimes very expensive, most of the times actually, and it takes a very long time. It takes a lot of GPUs, like graphical processing units, to train those models because they're very large. That's why they're also sometimes called large language models. And it's as I said, very expensive. But in order for other researchers to use transformers more widely, or the community, or anybody really, you can train those transformers and those very expensive ones, and then provide the models for other people to use, for other researchers or for anybody really. So, for example, Google would train a very expensive transformer on a lot of data, save the model, and make it available for everybody to use. Then you can take this trained model that was very expensive to train, and you can train it again on a little bit of specialized data, like specific data that you're interested in. Case that's what we called transfer learning, and that's what we also call using a pre-trained model. So in this case here, GPT is also pre-trained on other data and then reused and more fine-tuned on more specific data. And transformer here, of course, because it's a transformer model. GPT-3, for example, was trained on 45 terabyte of data. That gives you a rough estimate on how large those data sets are, and that's textual data. 45 terabytes of text is a lot of data. So what are transformers and how do they work? So if you wanted to place transformers or large language models, if you think about the artificial intelligence as this blue bubble here, as this huge area that has many sub-areas, that's the red bubbles, then one of those bubbles would be natural language processing, and that's where language models are based and where they were developed. Other areas from artificial intelligence kind of took a look at the language models, and they spotted that they perform really well on certain tasks. So as it happens with many areas, if someone sees something that performs really well, they take it and apply it to other areas, for example, computer vision. But we're going to talk about this in a few minutes. So transformers are really good in classification tasks. They're very good in summarization tasks, so text summarization. They're also very good in text translation tasks and many others, for example, question answering and so forth. But how do they actually work, and why are transformers so popular? Well, to answer this question, we have to take one step back and think about how transformers use their data. So we're talking about language models here. That means we're dealing with human language, and language have words and sentences. So and those have an order. So the order of the words is important. So we're dealing with sequential data here. And you can't just shuffle the words around because that would change the meaning of those words. But those models also need to learn what word order is and to understand the meaning of that and the context. So here, for example, if you take a sentence like Captain Janeway hunted the Borg, if you change the order of the words to the Borg hunted Captain Janeway, it changes the meaning of the sentence. And that's why it's so important that language models understand the word order. So to take a step back, before transformers came along, there were many other models. And one of the most predominant ones were recurrent neural networks and long short-term memory LSTM models. So one is the RNNs and one is the LSTMs. So recurrent neural networks have an issue called vanishing gradient. So that means that information is lost over time when it is processed inside the models. So the models will see the data many, many times, and over many iterations, some information will just simply get lost, and this has an effect on how the model performs. Other machine learning models have that issue too, but this is just an example here. Another problem that RNNs had were they had really a difficulty in capturing long-term dependencies. What that means is if a model would read a very, very long text in order to understand the sentence, by the time it reaches the end of the sentence, it would have already forgotten the beginning of the sentence. So there were some significant weaknesses here with long textual data and the performance of this model. LSTMs then came along. They performed a little bit better, but they also had similar issues. They had limited memories. They also had the same problem with the dependencies. So again, by the time when they read the sentence at the end, they would forget the beginning. And also they had generalization problems for the more complex an LSTM model got. So what that means, the term generalization means in machine learning on how well your model performs on unseen data. So you train your model on one specific data. If you train it too much, you may overtrain the model, like overfit it. It's going to be very, very good, perhaps on one particular task, on this specific data that you train it with. But as soon as you take it out in the real world, it will perform very poorly. So generalization is very desired in machine learning, so that the models perform really well. If you train it on one data, then you take it out in the real world and it should perform equally. So before transformers came along, it's important to note that there's a host of other models that were used before, like gated recurrent units, GRUs, LDAs, or conditional random fields. Those models still have applications in various NLP tasks today. So they're still very heavily used in particular applications. And as with many things in natural language processing or in machine learning, if you have a particular problem, it's not very uncommon that you take parts of one model and you stick it to a different part of another model. So there's many architectures out there that kind of consist of different parts of those different models. So how do transformers actually work? Well, essentially, they are a neural network that receives a certain input and produces an output. Now, what's a neural network? A neural network is designed after how the human brain works. So it's inspired by the human brain that can learn and make decisions. It's made up of interconnected artificial neurons that work together to process information, identify patterns, and solve problems, allowing it to perform tasks like image recognition, natural language processing, and even playing games. So here the neurons are represented as these spheres. So you have input layers, hidden layers, and output layers. There's certain input that will propagate through this network multiple times, and with all the other mechanics that we don't need to go into now, this network would learn a particular task very well on a particular input data. So there's certain kinds of neural networks, and here you can see a convolutional neural network. This is a very popular kind of neural network in computer vision. So you can see the individual neurons here as the black dots, and they're connected to other layers of neurons. And the neural network would see an image here, for example, a cat or a dog. The image would be encoded and fed into the network, and only certain dots will fire, only certain dots will be activated by what kind of data is fed into the network, and they are connected to the next one, and it propagates through to produce in the end like a classification layer if it's either a dog or a cat. That is a very, very high level view on neural networks, but we don't need to go too much into detail here. That would be another video. So in the case of transformers, we have an input, we feed this input to a neural network, and we get an output. So here, for example, we have a text, a sentence, the quick brown fox jumped over the lazy dog, for example. It will be fed into the neural network and encoded and then decoded after processing. And here, in this case, we get the French version of this sentence as an output. But actually, transformers have many encoders and many decoders in there. We, again, don't need to go into details here now, but just to touch briefly on what's inside this transformer architecture, this gives you like a brief view in how a transformer works and what's included in that architecture. However, there are essentially three things that sets transformers apart from all the other language models. There are three mechanics we're going to talk about here now. One of them is positional encoding, the other one is attention, and the third is self-attention. So let's first have a look at positional encoding. So here we have the sentence, the quick brown fox jumped over the lazy dog. Again, we learned that language models need to understand what word order is, and they need to respect and learn the context of word order. Positional encoding will help them to understand this, and specifically here for the transformer. So in order to do this, we would add a numerical value of the order to individual words in a sentence. So and that's going to be adjusted in the data itself. So we wouldn't need to do anything fancy inside the transformer model itself. We just add the positional encoding to the data that we have. This is part of the process when the data is fed into the transformer. So the positional encoding is added to the data, and that's how it learns the order and the context of the words. Talking about word order, now is probably a good moment to highlight one of the most famous transformer models that have been developed, and that is BERT. Not this BERT, but yeah, this BERT. And BERT means here basically pre-training of deep bidirectional transformers for language understanding. There's a very important word in there, that the bidirectional means that these kind of transformer models are also able to not only read sentences from left to right, but they read the sentences bidirectional, so also from right to left. And when this model was introduced, subsequent models kind of acquired this ability of reading language in bidirectional ways, and that improved their performance as well. That is another reason why they got even better. Okay, so the second aspect why transformers are so good and how they work is attention. So here's the original paper, Attention is All You Need, that kind of introduced this mechanism and highlighted transformers. So what does it mean? So here you can see two sentences in two different languages. So one on the top is the English version, and on the right Here you can see the French version. And the graph in the middle shows you the overlaps of where the model looks at. This is kind of the attention graph. The curious thing here you may spot is that we have kind of a flip here in the middle, a negative attention. And that is due to that the words, the European Economic Area, is actually flipped in French. So it's Zone Économique Européenne. So the words are flipped, and hence also the attention is kind of reflected here. So the third aspect is self-attention. Neural networks learn aspects of the data over time. So they see data, the same data many times over, and they learn. And each time they see the data, they learn internal representations very well over time, such as gender or synonyms and so forth. Self-attention allows the model to kind of put an importance on the different words in a sentence. So based on the relationship of the words in a sentence with other words, the models can weigh this and therefore learn the context in that sentence. So it enables them to focus on the most relevant information in a sentence and for a given context. And overall, this leads to better performance and its understanding of those representations of the input data. So let's have a look at an example here. If you take the sentence, "The quick brown fox jumped over the lazy dog," the model here probably would focus on jumped or dog, and hence learn the context that this is an animal here. If you look at the fox here, if you consider the fox as the context we want to learn. But for a different example, for example, Fox News reporter Gordon Devereux quit his job today. Here the model would probably focus on the contextual words of news and reporter. So fox here means something different than fox in the other sentence. And this is what self-attention helps the model to understand over time. Okay, so we learned about transformers, a bit of the history of them and on a very high level overview on how they work. But transformers in health, so these are language models. How can they be useful in healthcare or medicine? Well, in one area, for example, they can learn electronic health records. They can process them, they can highlight and summarize them, they can answer questions for certain treatments, they can classify text. So there's a broad area, application area, where transformers and large language models can be applied to. Another area is medical imaging, for example. Now you may think, imaging, we talk about language models here, right? Well, as I highlighted earlier, if in one area something works really well, then other machine learning areas in artificial intelligence may think, perhaps we should grab this model and try it ourselves. And that's what happened. So computer vision had a look into the language models, particularly transformers, and they are currently very popular in this area too and applied to imaging tasks like finding tumors, identifying certain areas in MRIs, for example, areas of interest. So let's take a look at a particular example here for transformers and how they can be useful and applied in healthcare and medicine. For example, let's have a look at classifying medical studies. So on the left, you would see, for example, clinical researchers. They are interested in the most dominant treatment methods, the best treatment methods for a particular issue, for a particular problem. For example, stroke. So clinical researchers would search or comment studies on what treatment is best for strokes. Then they would publish them, and those studies, those published documents would be indexed somewhere in a database where all the other clinical researchers could have access to and get the information and have a look on what's the best treatment method for a particular issue. So on the right, you see here PubMed. PubMed is a public database for medical studies, And here we see a search result for strokes. So you see all the beginning of a lot of studies listed that look into stroke research. So if you took a closer look at this search, you may find on the left-hand side there's a little tick box for example, clinical trials, or for books and documents, or for randomized controlled trials. Now, what's a randomized controlled trial? Well, an RCT is a type of scientific study where participants are randomly assigned to different groups, here A and B. One group, for example A, receives the treatment or intervention being tested, while the other group, B for example, serves as a control group, receiving either a placebo or an alternative treatment. This design helps researchers compare the effects of the intervention objectively, and it determines its effectiveness by minimizing biases or confounding factors. So those studies will be commenced by medical researchers, and then the results will be written up in a medical publication, a medical document, as we've seen earlier. And that would then be indexed in those databases. So how can transformers help here? Well, if you think about a procedure, if you wanted to know what's the best treatment or not, or if a study is even an RCT or not. In this case, we saw this checkbox earlier, so we're classifying here for RCTs or not. Then a procedure would be for a pipeline to extract the text and feed it into a transformer. The transformer would then look for certain keywords. Sometimes in the documents there are keywords directly mentioned, such as trial or random or RCT. It will again learn the context in the sentences, in the words, and it will then identify those articles as RCTs or not. Similarly, all RCTs have a particular structure to them, which is called PICO, Population, Intervention, Comparison, and Outcomes. Like, what's the study groups, how many groups, what's the population of a study, what's the intervention, what treatment has been applied, for example, a new drug or a new vaccine. What's the comparison study here? What's the comparison, like the control group? And what are the outcomes, of course? And again, transformers can learn the context in the sentences from the different words and therefore can pick up on those elements really well. Aside from this, there are transformers in other areas. We heard that earlier, briefly, when we looked at medical imaging and transformers being applied in computer vision tasks. So, for example, there's a certain kind of transformers now very popular to do exactly that, and they're called vision transformers. You can see the architecture here. You may spot that similarly, we also have positional encoding again. You see the numbers attached to the data. But how are images actually processed? You may think of, how is a language model actually dealing with images here? Well, the trick is we chop up the image, and you can see it's then fed like the words, like a sentence. As you can see, think of a sentence of images here fed into the model, and then the positional encoding is again added to the sentence, and then it's fed into the transformer. Again, attention inside and self-attention will come into play, and that's how transformers work. Okay, then there are also transformers for segmentation tasks, for example. So here you can see a segformer. This is a recent model that's really focusing on finding different items in videos or images, like here is an example from a self-driving car. There's also transformers for music generation. So here you can see a graphical representation of the relationships between the tones of the music transformer playing piano. And there are many more transformers out there, hundreds, if not thousands. Many of them are available on a platform called HuggingFace. This is a company that focused on making natural language models accessible to the research community, and they were very successful with this. They act like now as kind of the central hub for a lot of NLP research and NLP researchers. You You can see here is an overview of the models that they have on their platform. So they have models, data sets. You can even deploy models on their websites. We see this in a minute, but here you see an overview about different kind of models on the left, ranging from object detection to video classification to text summarization, all specialized in those tasks. And on the right, you can see a list of models that are trained and fine-tuned. Again, we touched fine-tuning earlier, where large companies train expensive models. They would upload it here, and you can download it by yourself and fine-tune it on specific tasks that you're interested in. To give you an example, I can demonstrate one of my transformer models that's on that platform that I created for the NASA Solar Dynamics Observatory. This transformer is called SDOVT1, and it's focused on classifying Solar Dynamics Observatory data. What that means is there's a spacecraft that's called the Solar Dynamics Observatory. It's positioned so it monitors the sun 24/7, and NASA collects data from the sun. So it monitors the sun for specific, for radiation, for specific sun events. And this vision transformer is very good in classifying 3 different solar events. One is a coronal hole, the other a coronal loop, and a solar flare. So let's have a look at this. So here we are on the HuggingFace platform. You can find the model by searching for it here, and here's the name SDOVT1. You find a model description here. You find example images of those 3 classes. For example, here's a coronal hole, then a coronal loop, and a solar flare. There's more descriptions here, and this is the little code snippet that you could copy and paste into a free Colab notebook and use it by yourself. But there's more to that, to this platform. So up here, you can see a host inference API. That website here actually has a deployed version of my model, so you can immediately try it. If you grab this image here and download it, I already have some here on my desktop, so I just drag it into the inference API, and the model loads, and you can immediately test the model and see some example outputs. As you can see, it correctly classified this one with 87% accuracy. The model thinks that this is a coronal loop. But again, this is a vision transformer model. If we go back to language models, there are many examples up here in the model repository. And if you just click on a particular one here, GPT-2 for example, you also see there is the text generation option here where you can test those models for specific tasks that they were designed for. So I hope this short video about transformers, how they work, and this brief overview on the intricacies of transformers and the mechanics behind them and why they are so popular was interesting. And feel free to get in touch if you would like to know more. Thank you very much.